Lecture 7.4, two-slit interference. Here's the overview of interference that we're going to be looking at. First, we want to look at the conditions to produce steady and consistent interference patterns. Two, then we're going to look at the two-slit pattern itself. And then we want to calculate the screen location of fringes. 4, we want to determine the interference pattern in detail. That is, we need to be able to calculate all of the number of bright and dark fringes. And then finally, we want to calculate the relative intensity anywhere in the interference pattern. So let's start off with the first thing. There are two requirements to be able to see a consistent and steady interference pattern. The light source must be monochromatic and coherent. And those are the two things that we want to look at. Monochromatic light is of a single frequency. And a lot of times people will say a single color. Whereas polychromatic has multiple frequencies. For example, an LED. An LED, like the light bulbs in your house, are polychromatic. So as an example of this, we could think about the white light from the sun or a light bulb. Again, it could be an incandescent, it could be an LED. So the white light from the sun has a continuous distribution of multiple frequencies. And if we just look at the sun spectrum, for example, let me show you this image. Here's an image of the sun spectrum, and you could see that its range goes from around 380 nanometers to around 700 nanometers. So when you start to look at this, we can imagine the following scenario here. If, say, blue and red light overlap, then we're starting to look at something like this. So if I have red that looks like this, and then I have blue that looks like this, it is true that these waves are overlapping, but interference patterns are not going to really work very well. So if they overlap, we will not get maximal constructive or destructive interference. We're just not going to get it, not, at least not in a consistent way. So polychromatic light will not produce a consistent and steady interference pattern. On the other hand, monochromatic can produce consistent, produce a consistent pattern. And if I look at this a little bit more detailed here, so if it's polychromatic, and what I'm going to do here is that I'm going to draw these with different colors, but remember, it's a single frequency. The colors are only here to really separate the two waves, but you could imagine that if I had waves that were moving like this, is that so just under, good circumstances, we could get a situation where we can have this. We could either have these waves overlapping in phase or these waves being out of phase, which in this case, this will give us a bright fringe. And then here, we would get a dark fringe. The most common monochromatic light source is the laser. So lasers are easy to get, and therefore that's the most common. However, monochromatic light is still not enough to guarantee a consistent pattern. And the question is why is that? Now, what we'll do here is that let's use an old incandescent light bulb. Why? Because it's a little bit easier to explain. So consider an old incandescent light bulb. It's a piece of heated metal. And here, it's the metal that's typically used is tungsten, where the vibrating electrons produce or emit electromagnetic light or emit light. The problem is these emitted lights or emitted waves change their phases quickly and randomly. And the reason why that is here is because the electrons and metals move in a random way. This source of changing phase is called incoherent. So in other words, if I have an incoherent source, that means that the waves keep changing phase, and so therefore you get no consistent pattern. However, if you have a coherent source, then the waves do not change phase. And therefore you get a consistent pattern is absorbed, not absorbed, but observed. We are charmed of the fact that lasers are both monochromatic and coherent, and will produce a consistent interference pattern. And that's what we need. So now we can then go on to a two-slit interference. We now know how to do this. So let's go look at this. So what we're going to find here is that in 1801, Thomas Young performed his historic experiment. That demonstrated that light was not a particle, but that light was a wave. Before that, Newton had a model that claimed that light was particles. But Young showed that you couldn't explain this nature of light without using waves. So Young used monochromatic light that fell on two closely spaced slits. Now, what you're seeing here is that, so he did not have a coherent source. But what he did here is that he had two tiny slits like this. And so what happens here is he sent in monochromatic light. Let's say that this light is coming in like this. Okay, so this was monochromatic. And as a consequence, when these waves came out of these slits, what you find out here is that this produced coherent light. He didn't have both, he only had one. And here's what he observed on the screen. He saw these fringes. So what you're seeing here is that this is interfering waves from the slits. And you could see here is that this tells you that this is a series of bright and dark fringes. So now what we want to do here is that we want to go and look at these details here. So what we say here is that in order to understand this, is that we need to learn the characteristics of interference. So the characteristics of these two-slit interference pattern are: one, we're going to need the M value of a fringe. In other words, we want to know what MC is. We want to know what MD is for some particular fringe. 2, we need the screen location of a particular fringe. So in this case, this fringe location is typically written as y of m, and or we need the angular location, which I'll label as theta of m. 3, we want a detailed sketch of the pattern So that's what I mean when I'm talking about the characteristics. So let's look at the setup here. So let's look at the setup of a 2-slit experiment. And this is what you'll be doing in your lab. So here's the required parameters. One, we need incident light, right? So this is going to be the incident light. So here's what we know. We're going to send in light. And all we know is that this has to be monochromatic. Because when they come out of the slits, it's going to be coherent. So the next here is that we need little d, which is called the slit separation. So when I look at a slit separation, it's telling me that I have something like this. I have narrowly spaced slits. So everything is opaque except for those little slits. And I'm going to define this guy right here as my slit separation, which is little d. Earlier, I did not put the wavelength in here. So what we're going to see here is that now I'm going to have big D, which is the screen distance. So to observe the pattern, I'm going to have a screen that's located right here. So that means that the distance from here to here is my screen. Now what I'm going to do here is that I'm going to have interference patterns due to these overlapping waves. So as they move, we've already said this already, but I'll say it again. These are two coherent light sources. Now, everything is going to be measured relative to what I'll call the central line. And so then the next thing here is that I'm going to have, this is going to be my fringe location on the screen. So that means here at some point, I'm going to have a fringe. And so what we're going to say here is that this distance from here to here is this location. Relative to the central line, this is going to have some angular location, theta m. So typically it's either the fringe location or I could have the angular location on the screen. So that is my interference setup here. So let's look at these locations here. So the interference fringes follow the path difference equation. And what that means here is that if I have a path difference between two waves, I can either have, as we've already talked about, if I have whole waves, I'm going to get constructive. If I have odd multiples of half a wave, I'm going to get destructive. Where, of course, MC and MD is going to be 0, plus or minus 1, plus or minus 2, etc. So if I look at this, we're really going to be looking at the paths of these two light sources here. And what you're seeing here is that when I look at this, here's what I'm seeing. So I imagine that I have a screen where I'm going to observe my interference patterns. So what do I mean by the path difference? So let's say that I have a fringe here. Now this could be a bright or a dark. So what you're seeing here is that this slit I'm going to call number 1. This slit I'm going to call number 2. So if you look at this thing, you can see here is that if I follow light from here to here, this guy I'm going to label R1. If I follow light from 2 to that location, this is R2. We clearly see here, okay, we see that R2 is greater than R1, which implies that R2 has to be R1 plus delta R. So what we're focusing on, when we draw this statement up here, we focus on this path difference. So let's look at that path difference. So if I look at that path difference, we could then say that we have constructive interference. So if I talk about constructive interference, what do I mean by the statement? If delta R is equal to 0, then that means that R1 and R2 travel the same path, right? So they travel the same distance. In other words, R1 and R2 are the same. So this really tells us that R1 and R2 are the same. So in the language of the M value, this is what we call MC equal to 0. And so this guy will then be located at the central axis. Now let's look at the next one. So if I look at the next one, delta R is equal to lambda, then we clearly see here that R2 travels farther than R1 by lambda. So because this is one wavelength, we typically say that this guy is then going to be MC equals to plus or minus 1. Now, why is it plus or minus 1? You know what? I can't really show you that right now. It turns out that it could go above or below the central line. This location is what we call the first interference. And then I can just keep going on. So now if I have delta R equals to 2 lambda, then that means here it's really R2 is equal to R1 plus 2 lambda. It traveled a distance of 2 lambda farther. So then that tells us here that this is going to be MC equal to plus or minus 2. In other words, we call this the second interference. And I can do the exact same thing for destructive interference. So if I look at destructive, the language gets a little bit darker here, because now here what I can do is that I could have a path difference. By the way, I can also do plus or minus here, which I did not do, but that's what that means. This could be plus or minus half a wave. And then this is what we call MD equal to 0. So that means here, so if I look at this thing, that means that wave 2 is longer by half a wave. Now, we got to be careful with the language here. This is the first dark fringe. No, I probably shouldn't have been saying the first interference. Maybe we should go back and say that this is the first bright fringe. Okay, let's say this is the first right fringe. And the numbers add up because MC is equal to 1. And then here, the second bright fringe, you see that it adds up with MC. That's not the case with dark fringes. Okay. So then if I continue on, we're going to see here is that if I have a path difference of plus or minus 3/2, then again, R2 travels farther by 1.5 waves. And look at the MC value or the MD value. In this case, it's plus or minus 1. So guess what? This is not the first dark fringe, it's the second dark fringe. And so this is where we have to be careful with the language of destructive interference. So what I want to do here is that most applets don't have light coming out of two slits. So most applets that show interference have point sources, not slits. In other words, if I have a 2-slit like this, all I know is that as light is coming through this, I'm going to have light that's going to be monochromatic and coherent coming out of these 2 slits. They're overlapping. So here we look at slits. Many of the applets that we're going to look at are not going to be that. What they're going to be here is that they're going to be these point sources. And these point sources are going to be emitting waves in a very analogous way to the 2 slits. In fact, they're equivalent. One can't differentiate between the two. And these are going to be 2 single point sources. So what I'm going to do here is that I'm going to visualize the 2 slit pattern by utilizing one particular applet. Now, the power of this applet is that it explicitly shows the path difference between 2 waves. Nobody does a better job than this. So here's what we're going to see. So when I look at the organization of the applet, it's going to look something like this. Okay, here's how the applet is going to look like. The organization of this applet is what we're seeing here is that note that there are 2 sources right here. There's a source right here, and there's another source right here. So what I want you to envision here is that I have 2 slits right here. So this is acting like my 2-slit pattern. Now the screen here is not flat. It's actually rounded. So the screen actually goes something like this. This is the way the screen is. What we're going to do here is that we're going to assume that this screen here is actually located right here. Okay, so here's going to be my screen. And then again, here's my 2 slits. So now what's going to happen here is that we know that there are waves that are emanating here. And so the first thing that I'll look at is that I'm going to call this spot, this is constructive interference right there. So this region right here, this is where I have a region of constructive interference. Now, what you're going to see here, and the reason why you're seeing constructive interference is because you're seeing the crest and the troughs of the waves overlapping. So that means I have a wave that's looking like this. So this here is the bright, in this case yellow, and then here this is the dark. And that the bright represents the crest, the dark represents the trough. So the waves are overlapping at that spot. Now there's another region, which is this guy right here. And if you look, this guy right here, where it's blurred, is destructive here. And here you're seeing that these are regions of destructive. And so the regions of destructive are the blurted out regions. In a lab situation, interference patterns do not materialize like this. In order to do that, one needs a ripple tank. So, what we see is what we already showed, right? I have this image up here, which I'll just grab. And if I bring this image down here, here's what we see. We see this pattern right here. And so you can see here is that in this situation, that right there represents a bright fringe. This right here represents a dark fringe. So both views are important, and we're going to utilize both. So what I'm going to do here is that I'm going to use this wave interference. I call it wave interference 1 applet. And the thing about it is that they have an HTML5 version. But if you download it, it's considerably better. So now I'm going to label the structure of the fringe patterns. And I'm going to start off with constructive interference. So here we go. So the first thing I'm going to do is I'm going to deal with constructive. Okay, so what I'm going to do here is that I'm going to isolate each of the MC values along with their locations in the interference pattern. So here we go. So let me go share my screen. And here's the pattern right here. So what you're seeing here is, again, you could see that I have two sources of waves and they're moving out. We see that this area right here is constructive, the blurred out is destructive. Now, let's look at this. This is what's beautiful about this. So if I click here in the middle, you can see here, right in the middle, I have two waves that are in phase. And look at that. Look at the black dots. They are traveling the same distance from the source to where I'm looking at this. Now, look what happens if I go to the next bright spot. Look at that. You can see that wave 2, which down here is the bottom, has a full wavelength that it has to travel. And if I go to the third bright spot, you can see here that this is two whole waves path difference. Now note, I was going upwards, but what happens if I go down? If I go down and I click here, look at that. These guys are also waves. So to differentiate between going up and going down, we have plus and minus. And if I go to this one, you could see here again that that's two wave difference. That's the power of this applet. So what I want to do here is that I want to go and show you what is it that we just saw. So what I did here is that I took a screen image of these guys, and here's what we see. So let me move this over here. And what you're seeing here is that in this case, the path difference between the waves is 0. The path difference in the second case, where I have a bright fringe, that is one wavelength. And note, this is where we're seeing it right here. There's one wavelength right there. And then the path difference here is two waves. Again, we're seeing two waves right there. So immediately, when we see this, this immediately tells us then that MC must be equal to 0 here. Now, this immediately tells me that I have MC, but note that there are two values that we want to look at. Not on, so right here, I'm going to write it right here. This is MC equal to 0. Now, let's look at what happens when I go up here. If I go up here, this is now going to be MC equals to plus 1, right? But note, down here, I have MC equal to minus 1 too. So there are two locations where the path difference is there. And then finally, if I go to the second one, that immediately tells me that this has to be MC equals to plus 2. Again, this is MC equals to plus 2, but down here, I have MC equal to minus 2. That's where the plus and minus signs come in. So now, you're seeing that I'm starting to develop a pattern for bright fringes. So in illustration, of the pattern of bright fringes looks something like this here. So I have a screen. So I'm going to make my screen nice and thick. Nope, that's not what I want. Here, let me make this one thicker. So imagine that I have a screen that looks like this. Okay, there's my screen. So now what I'm going to do here is that I have a central line. There's my central line. And right here, I'm going to have my screen right here. So again, this is my screen. Nope, I don't want to write it there. This here is my screen. And what I'm going to do here is that when I look at my fringes, I'm going to produce a series of bright fringes. And so what I'm really looking at is that I'm looking at something like this here. I have one wave that goes from here to there. And this will be R1. I have a second wave that also goes to the same location. And this is R2. So you can see that R2 is greater than that. And what we're seeing here is that if I look at this, that means that R2 is equal to R1. Oops, that's not what I wanted. R1 plus some delta R. So what we're seeing here is that I'm going to label these as MC. Then I'm going to look at the path difference, and then I'm going to look at the phase. So this is what we call 0, plus 1, plus 2, minus 1, minus 2. And then that tells me that the path difference to go right at the center is 0. Then this will be 1 wavelength, 2 wavelengths, a negative wavelength, 2 negative wavelengths. And then if I start to look at my phase for constructive interference, we saw that the phase had to be multiples of even pi's. So this is sort of like, this illustration shows you how we're starting to label these points here. Okay, that's what I mean by the bright fringes. Now I can do the same thing for destructive interference. So here I'll move a little bit faster. So now if I look at my destructive interference, so I'm going to say that this is similar to constructive, right? So now let's go share my screen. And here we are. So it's the blurred out spots that give you destructive. So I'm going to click on the dark spot here. And now let's freeze. Look at the path difference. It's half a wave. Okay, it's half a wave. That's a dark spot. Now, no, if I go below, this is also half a wave. So you're seeing this pattern that comes up. Now, if I go, so this is the first minima, and this is the other first minima. This is the second minima. And if I freeze that, look at that. That is actually 1.5 waves. It's not 2 waves. And if I go down to the second one, below, you could see that that's also 1.5 waves. And then finally, there's one up here that we could see here, and this turns out to be 2.5 waves. So if I go back to my screen and show you my screen capture of what I just did here, I'm going to go and I'm going to paste this guy in here. And this is what we have. One, we have two dark spots that are labeled that have a path difference of half a wave. And you can see here is that this right here is half a wave difference. So this guy is then going to be MD, and look what I'm going to do here, plus 0, and this is going to be MD minus 0. I know that 0 doesn't have a sign, but it's to remind you that there are two cases for MD equal to 0. Now, if I look at the path difference here, this is 3/2 of a wave. So in this case, this is MD equal to plus 1. And then down here, this is going to be MD equal to minus 1. So you could start to see how the pattern starts to go here. And then over here, we have a path difference of, remember, they're odd half multiples of the wavelength. And this guy here, this has to be MD equals to plus 2. And then this one here is going to be MD equal to minus 2. So if I start to look at my pattern, it now really reads like this. This is MD equal to plus 0, MD equal to minus 0, MD equal to plus 1, MD equal to minus 1. So we're seeing this pattern. So what I want to do here is that I want to take this and I want to copy this and I want to summarize this here. So now up here, we want to illustrate the pattern. Okay, so now what we're going to do here is that we're going to illustrate the pattern for destructive. So if I click this guy here, now here's what I'm going to do here. So in this case, instead of green, I want that black, right? Because these are dark fringes. Oh, I can't put those there. Ooh, I got to erase them. That's not going to work. So here's what we're going to do. These do not land on the central line. They're off the central line. And so what you're seeing here is that instead of MC, I'm going to call this, here, I'm going to make these all black. I'm going to call this MD here. So what we're going to see here is that we're going to have that this is plus 0, minus 0. Again, 0 doesn't have a sign. But just to show you that there's symmetry in what you're seeing, then this will be plus 1. this will be -1. And if I had more, let's say if I put this guy right here, this would be -2. And then up here, this would be +2. So if I look at the path difference, this gives me a path difference of 1/2 lambda. This is -1/2 lambda. This is 3/2 lambda. This is 5/2 lambda. And these are all the positive values. And then here, this will be -3/2 lambda, -5/2 lambda. And then the phases are odd multiples of pi. So this would be plus pi, minus pi, plus 3 pi, plus 5 pi, minus 3 pi, minus 5 pi. So the organization looks like that for destructive interference. So now, if I was to now combine both of them, we get something like this. So I'm going to set up my two slits. So I'm going to come in, and it's going to look something like this. So I'm going to go, and then I'm going to have my screen over here. I'm going to have my central line. My central line goes right here. And so now I have a pattern that looks something like this. There's a central, and it's going to look something like this. And in between, I have dark fringes. And so if I start to look at this, you could see here is that I have an MC value that's going to read 0, +1, +2, -1, -2, -3. And then I have an MD value that are off, right? These guys are offset of the MC values. So then this guy gives me +0, -0, -1, -2, +1. So if I start to look at the path difference between these guys, here's what we find. The path difference for this here is going to be 0. This is going to be 2 pi. This is going to be 4 pi. This is going to be -2 pi, -4 pi, -6 pi. And then the blacks here are then going to be pi, 3 pi, -pi, -3 pi, -5 pi. So you could see the pattern as it starts to occur.